Good afternoon and welcome to today's electronic design webcast. Our topic today is getting the most out of DDR4 and preparing for DDR5, sponsored by Keysight. I'm Chris DiMartino with Informa's Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now let's meet today's speaker. Perry Keller is the team lead for Keysight Technologies' Digital Applications and Standards program and manages its Memory Applications program. He represents Keysight on the JEDEC and Universal Flash Storage Assistant Boards of Directors and is chairman of the JEDEC JC40.5 and JC64.5 Logic and UFS Validation Committees, as well as the UFSA Compliance Committee. Perry joined Hewlett-Packard in 1980 after graduating from Rice University with a master's degree in electrical engineering. As HP's TMM group evolved into Agilent and then Keysight Technologies, he has served in project management, architecture, and R&D roles for hardware, software, and ASIC development, as well as marketing and product planning for high-performance instruments and applications. He lives in Breckenridge, Colorado, and enjoys skiing and mountain biking. Now let me turn things over to our presenter. Perry, the floor is yours.
Okay. Thank you, Chris. So today I wanted to talk about what's involved with getting ready for and getting the most out of your memory channel designs and memory subsystem designs with DDR4, and then what you need to think about to prepare for the next generation. I get a lot of questions from folks along the lines of, when is the right time for me to consider making the jump to the next generation of DRAM, and I also get a lot of questions, especially with DDR4, starting with DDR4, about actually what the meaning of the spec is, because there's new things that have been coming up, starting with DDR4, that have really challenged the industry to understand and implement properly. And so today, in this talk, I want to try and demystify that as much as possible so you can get the most out of your designs. So for quite a long time, memory technology has lived in a fairly comfortable space of high-speed digital design. This started with the first DDR, for sure, and its big innovation was the source synchronous clocking, which was new to a lot of folks, but is basically the launch of about 15 years of high-speed digital memory interfaces, and that technology worked very well for DDR1, DDR2, and DDR3, although when DDR3 started to get into about 1600 megabits per second data transfers, some chinks were starting to show up in the armor, and specifically the timing margins were collapsing because of things like random jitter, which really weren't allowed for in the spec. And so for DDR4, it was decided that these kinds of issues really needed to be taken on directly. And so for the first time in DDR4, you saw the spec change fundamentally from the way it had been written for the last 15 years, going into what I call the serial speed domain. You can see here, of course, the I, as you go faster, gets smaller. And the way that that is dealt with is by taking advantage of knowledge that's been gained in other higher speed technology areas, and then applying it to the unique environment of the memory subsystem. Now, that was and it still is a transition that's being digested in the industry and by the users. But going beyond that, of course, the I is going to still get smaller, and it looks very much like another revolution, another radical change in how the spec is written, how designs are done, and how measurements are done. Is going to be necessary to go beyond DDR4. So after about 10, 15 years of living in the comfort zone just when you thought it was safe, now we find that the rules are changing almost with every generation. So the key here is to embrace that and get ready, understand the changes, and get your game on for the next generation DRAMs. So let me go into a little bit more about what I mean by high-speed serial, serial speed, hyperspeed, and so on. Because, you know, at least when I was in school a long time ago, virtually everything that you did in digital world was what we would call now low-speed digital. And the big data sheet attributes we worried about were things like fan-out and capacitance. And that's still true in some memory technologies, such as the slower flash memory technologies. But then you reach a certain point where you can't ignore the fact that the signals, the interconnect, transmission line, and you have to take that into account in how you do your designs and how the spec is written. So this means that instead of worrying about simple numbers like fan-out and capacitance, now you just have to be thinking about timing, managing impedance discontinuities on the interconnect, IV curves for the drivers and receivers, which translate into termination impedances. And this is the comfortable world that we've been in for quite a long time with DDR1, 2, and 3. The thing that changed with DDR4 is that because things like random jitter, random noise were basically consuming the entire budget and weren't accounted for in the spec, we had to figure out a way to describe the memory device so that the I could be managed. You could make sure that there really was going to be an open eye at the receiver. And so the technology that was drawn from was basically other high-speed serial interfaces, starting with InfiniBand, but now they're very common, things like USB, serial ATA, PCI-Express, and so on. In this realm, you don't think about things like timing, setup and hold times, like you did with high-speed digital. You still, of course, think about transmission lines, and you want to maintain that kind of signal integrity. But the way that you need to think about the signaling at the end is with the I diagram itself and the concept called an I mask, which is not one-dimensional like setup and hold, but it's two-dimensional because it deals with voltage and timing issues. And the big thing here that threw people for a loop in many cases was that it became a statistical spec. With high-speed digital, DDR3 you would have things like setup and hold time. If you met those numbers, then the spec said you were guaranteed 100% reliable data transfer. Now, I think most of us know that in reality that really was never true, although for practical matter it was. It certainly is not when we got to DDR4 speeds. And that's why the spec and the measurements that support it and the design tools, the design concepts that you use for DDR4 had to change so that they could deal with these kinds of statistical, probabilistic descriptions of the waveforms and the eyes. Now, that's been proven and has been used now in memory for a few years, and for even longer, as I said, in areas like PCI-Express and USB. But to go faster than 3.2 gig, which is the goal for the next generation memory, it's quite likely that this eye is going to close. So right after having to make this big jump from high-speed digital, looking at timing and managing skews and things like that, right after having to go from that to dealing with the statistics of eyes and eye masks and bit error rates and things, now the eye's going away in the worst case. So what do? Well, again, the industry can draw on other technologies that have had to deal with this kind of problem for a long time. And the latest generations of PCI-Express are an example of that, where there actually may not be any place in the system that you can probe physically and see an open eye, and yet you have to be able to move data from point A to point B. Now, that's something that is understood with JEDEC, but the question is, how do you apply that in a memory environment? Now, nobody really knows what's going to come next, but it's quite possible that at some point, even the techniques used to open eyes up with equalization, preemphasis, will not be enough, and we'll have to go out and borrow from a broader domain, perhaps from data communications, using things like what are called complex modulation, and you get into whole new concepts. So here, after 10, 15 years of stability, it seems like with each generation, it's likely that we may have to make a quantum jump in the concepts that we go after. So let me show some examples of how this worked, just to put everything into context. So in the good old days, you'd have a relatively open eye, and you would think about waveforms over time. And so in the lower left here, here's an example of, say, the relationship between data strobe and a data line, and the spec would be describing what the setup and hold time is of that strobe of the data line, DQ, compared to the data. Other ways that you would visualize and characterize and debug designs is with timing and state analysis. So in addition to oscilloscopes, logic analyzers were really very important tools for everything up through DDR3, and they're still used up to DDR4. But when you're dealing with high-speed digital, timing diagrams are really the way you think. And so timing analysis, and then one step up to the protocol level to state analysis. This is the domain that we've all been living in for quite some time, and it's very comfortable. There's additional tools that are used here, such as, and this is where things like test automation came in with the use of more sophisticated software in the instruments that would do understand the spec and do automated testing for conformance and measuring margins against the spec. So again, what was done with DDR4, and this also affected LPDDR4, is that instead of a timing diagram describing the interface, the receivers on the memory were really defined by what are called I masks. And so here you see actually an excerpt from the DDR4 spec that talks about the I mask. In many ways, this is a simpler definition than setup and hold, because there's, although the clock is not embedded, it's the responsibility of the controller and the memory to work together to identify where the I actually is open at the DRAM, and then use training sequences to figure out where the controller can place the open I so that the signal can be received properly. There's a lot of complexity there, which is why training sequences have become more complex. But when you look at the actual core part of the spec that this is trying to deal with, it's actually a lot simpler than the maze of timing diagrams that we were used to dealing with. So this is something that people developing training algorithms find much easier to use. One of the big problems with up through DDR3 is you remember all the slew rate derating tables, and those were always a very difficult thing to identify. It was kind of an approximation to it was an approximate solution to this problem of what happens as a signal gets faster and the I shrinks. Slew rate derating was a way of trying to map that onto a traditional high-speed digital specification. Going to a true serial speed statistical I eliminates the need for that, and also recovers a lot of timing and noise margin that was just ignored in the previous specs. So here we talk about just what it is that, why it is that an I is the right way to describe these kinds of signals. And again, this gets to the fundamental difference between the traditional high-speed digital and this high-speed serial type domain. When you had a setup and hold spec and said, if you meet this spec, if you meet this setup time, you meet this hold time, you're guaranteed that you're going to get a reliable data transfer. That's basically equivalent to saying that there's a single point in the unit interval, a single point defined by the reference voltage and the transition of the data strobe, which is where the data is sampled. And so you have to make sure that given all the skews and variations in propagation delay that can exist inside the memory device or the buffer, that the signal that you're sending is going to be stable at that point inside the memory. Well, I think we all know, of course, that there's actually a data ballad window. There's a metastable region for each flip-flop. And so that means that that point isn't exactly fixed in time, but usually it's a very small amount compared to the overall timing of the system. When you start having to deal with things like random noise and random jitter, however, what you find is that that relatively fixed point starts to move around. And this is caused by things like noise. Oops. This is caused by things like noise and jitter, jitter converted into noise, noise converted into jitter, that have the effect of changing in real time the effective reference voltage and changing in real time the sample point, the point in time where the data is sampled. So that point that used to be stable and reliable actually moves around a good deal, and it's the boundaries of where that sampling point can move that define what the data mask, the I mask, looks like in DDR4. So when doing designs with DDR4 and then trying to characterize how reliable your system's going to be, a lot of folks really focus on margin. And of course, you want to have a design that's got margin in it. In the past, margin would be defined by how much actual setup time you're providing beyond what the spec requires and how much hold time you're providing. Whether you've got, whether your voltages are exceeding the VIH, VIL, AC, and DC especially. All of that stuff is now subsumed basically within the I mask. And because of the statistical nature of the signals, and because that's really accounted for, allowed for in the DRAM spec, what you have is instead of, say, a zone on the right or the left, that's just defining time margin, and up and down defining voltage margin, what you have is a region around the I mask that defines how much receiver margin or stressed I margin you're providing to the receiver. So here you see a typical oscilloscope capture using a color-graded infinite persistence capture of a signal. And you can see that depending upon the colors, the green areas represent areas where the signal is found less frequently. And then the hotter areas, the red areas and white areas, represent places where the signal is seen a lot. And then in the middle is this black area, which ideally is where the signal's never found. And as long as that is around the outside of that yellow mask, you can expect to get a reliable data transfer. Well, in fact, because RJ, random noise, random jitter are really unbounded mathematically, that means that in reality, that black region inside is never really closed. I mean, it's never really completely open. It's always closed to some extent. The question only is, how close do you get to the mask, that yellow zone in the center, before the probability of the signal encroaching that area gets too high? And that's why the DDR4 specifications basically said that you need to make sure that that the probability of getting of your signal encroaching that yellow region is less than 1e minus 16 if you want to guarantee that the DRAM is going to receive the signal. Actually, the spec says that you need to stay outside of that yellow region entirely so that the DRAM will receive it with a 1e minus 16 error rate. So the goal here is to provide a big enough eye with enough headroom around that receiver mask in the middle in order to make the chances of violating the mask really, really small. And so for DDR4, instruments needed to start providing the ability to figure out just how wide was that region beyond the mask. And design tools and your design budgeting needed to take into account how much RMS, random jitter, and noise was being produced in your system so that you could figure out how close you would realistically get to that I mask. These are all very different concepts than we've had to apply in the past. Now let's turn to this next case where we're dealing with a new generation of memory where the I, in some cases, is probably going to go away completely. So this represents yet another fundamental paradigm shift that designers need to be able to understand, embrace, and deal with. And so the most obvious analogy here is with PCI-Express Gen 3, where they grappled with this problem of the signals being fast enough with the loss on the channel that the eye at the ball of the receiver device or at the edge of the PC board was going to be closed, and they had to figure out some way to open that up so that you could get reliable data transfer. And so the main strategy that was used there was equalization. If you look at the evolution of DDR4 over time, each time a new speed bin spec was added, there was usually some kind of enhancement or additional training that was needed, or some kind of an update to the spec that would allow you to find an open eye if there was an open eye at all. But in all cases, even up to 3.2 gig, at the ball of the DRAM, the eye is always expected to be open. For the next generation, for DDR5, that assumption going away, they needed to think of something new to put in there. And pretty much the only thing that hadn't been thrown in to DDR4 yet was equalization. Now, there are folks who implemented it behind the scenes to improve their performance. But the first technologies to really use these kinds of approaches were the high-speed serial ones, with things like preemphasis and equalization at the receiver. Now, if you're looking at the entire channel going from the transmitter to the receiver, you can run simulations, you can do the math, and you can see, because PCI-Express Gen 3 actually works, that that this is an approach that has real promise. There's some realities, though, that you run into when you're trying to apply this to a memory interface that need to be taken into account. In PCI-Express, the receiver is actually quite intelligent. And it is in control of the training sequence that is used to basically figure out what the equalization factors need to be and whether some additional preemphasis or deemphasis is needed by the transmitter. It uses a combination of basically a CTLE, which is a linear equalization, and decision feedback equalizer, which is a discrete or nonlinear equalization. And there's various adjustments to those that need to be set in order to compensate for the loss that exists on the channel and open the eye up before it gets to the flip-flop that you can see there in the merge block on the right. There's also in PCI-Express a clock and data recovery unit, because while there is a separate reference clock that's supplied on the bus, it's not really the one that is used to time the actual data transfer. That clock is embedded in the data itself. Reference clock is used just to keep things as a general clock for the logic, and also to be able to help deal with things like spread spectrum clocking. But the receiver, in order to make this work, it needs to be able to know whether the eye that it's seeing is open or not, and it needs to be able to figure out, based on that, what kind of adjustments to make to its own equalization settings. And so the sequence is, it will get sent a training sequence by the controller, and it'll make the best I out of that it can. And if it thinks that it's not good enough, then it will send a signal to the controller that says, try some different settings on your transmitter, maybe some more de-emphasis or pre-emphasis or something like that. And then it will examine the signal again and figure out how good it looks. In the DRAM realm, these functions for figuring out what the equalization de-emphasis settings are and actually how you would, and actually measuring the error rate or the quality of the signal, those are sometimes very complicated functions. They can be very IP sensitive, but they're not simple circuits. And in DRAM technology, putting more logic on the DRAM is usually a bad idea for a couple of reasons. One is that the DRAM logic process the DRAM process just isn't very good for logic. And the other is that there's a lot of DRAMs out there, and there's usually only one controller per channel, which means that moving any functions, especially if they're logic intensive, out of the DRAM and into the controller will improve the cost of the entire system and its performance by a significant amount. So if you're going to apply this kind of a technique to memory, there's those economics that you have to consider, and there's things that traditionally you would think of as living in the receiver for all the high-speed serial interfaces that now have to move out of the receiver and into the controller. Now there's another important factor here when you get into this kind of equalization in the receiver is, where do you actually write the spec? So one of the big issues that the PCI-Express had to grapple with when going to Gen 3 was this idea that the so-called compliance point was no longer physically accessible for measurement. So it really wasn't possible to do, say, attach a scope or a bit error rate tester and calibrate all of that to have a known signal at the ball of the receiver package based on having an open eye, because the eye there would be closed. The only place that there would actually be an open eye that you could write a reasonable spec against was inside the die after the equalizers. But that's not a physically accessible point. And so there were a lot of work went into coming up with the mathematical concepts and the practical procedures to figure out how can you write a spec that mandates a certain kind of behavior at some point inside the die and yet make it a practical thing for people to be able to implement. And so this is the same kind of a challenge that next generation DRAM finds. And there are some signals where the traditional specification point at the ball of the package will continue to work. But there are places once the eye closes where that will not work anymore. And it's quite possible that the spec will have to be written again in a very different way. And this is a couple of examples of the monkey wrenches, if you will, that are being thrown into the mix when we go past DDR4. There's really a whole set of things that are different between memory interface and a traditional high-speed serial interface that need to be taken into account when figuring out just how do you do a design that runs faster than 3.2, and how do you specify a set of devices that can support that. Now, one of the few things that really is working in memory's favor here is that there is always a full rate clock that is provided to the memory or the receiver. So there's really no PLL that's needed in the DRAM, and that's good because those are very power hungry. But a significant difference between the two environments is that PCI-Express is really loss dominated. You've got very little crosstalk to deal with between the channels, whereas memory is notoriously dominated by crosstalk, and it's much more important than signal loss in generating iClosure. So there has to be more emphasis on crosstalk-oriented multi-channel interference impairments when specifying and characterizing the I. Another big difference is that DDR is bidirectional, and it's single-ended. As it's single-ended to save pin count, it's bidirectional as well to save pin count, which means that the read and write operations look different. There's a lot of advantages to not being bidirectional, and that you can properly terminate the bus. DDR is a multi-drop bus, so that there's really no theoretically perfect termination that can be provided because it's bidirectional. And so you've got things like ODT, which means that amplitudes will change between reads and writes depending upon where you're looking at it. Those things don't happen in a high-speed serial. On top of that is the burstiness of DDR. So each new generation of DRAM is more or less defined by how short the minimum burst size is. And so DDR4 had a longer minimum burst than DDR3. DDR5 is almost certainly going to have a longer minimum burst. But as long as it ever gets, it's almost always going to be less than what the designers of the high-speed serial interfaces worry about. They're looking at things on the order of power, major system power transitions. So concepts of things like an 8 or a 16-channel data burst, while they're being addressed in some of the newer standards like M5, are really quite a change for things like PCI-Express. And then finally, all of this has to work using a slow DRAM process. So again, this solution here, which has been proven to work for PCI-Express, for instance, to move data up to 8 gigatransfers per second, really needs to be adapted to the realities of DDR. And so here, this is what a equalizer-based DRAM technology might look like, where you've got the de-emphasis and equalization calculation values residing on the controller side, either in the state machine or firmware, along with the method of evaluating how good the I is. And then on the DRAM side, what you basically have is a naked receiver with direct access through mode registers to equalizer tap settings, just as you have had access to VREF offset settings, for example, with DDR4. So there are several implications to this that we won't have time to go into. However, it is because it's not high, because the receiver is in a sense less intelligent. It should be simpler to characterize, because now you've got individual mode register settings that will change very discrete behavior within the receiver. And then you can make measurements that are targeted on those changes in behavior. Basically, what's in the data sheet is going to be more or less directly accessible, instead of being hidden behind some very sophisticated algorithms. So starting with DDR4, but really for sure, as we go faster, there's new measurement science that's required in order to be able to do this characterization and then determine if the receivers and the transmitters, when they're all finished training, and think they've generated the correct die have actually created a system that can move data from one end to the other reliably. So while bit error rate testers have been used a long time in controller PHY development and verification, they haven't been used that much with memory. They've been used to some extent with the logic devices supporting memory. But for DDR5, it's likely that because of this new architecture, the measurement science that's related to receiver testing is going to become really central and critical to evaluating not only silicon success, but also how the system as a whole is working. And so this involves defining things like standard test fixtures and having the ability to generate precisely controllable ugly signals so that you can stress out the receiver. And then on the receiver side, on the DRAM or the DRAM support logic side, there needs to be a feedback signal that can report back to the instrument exactly whether it thought it saw a 1 or a 0. And that's fundamentally how you figure out what the bit error rate is. This is a feature that has not existed in anything, in any JEDEC standard up through DDR4. And so going forward, it's the kind of thing that is going to be very important. And it's something that is important not only to make the measurement, but it's important also because it involves connections at one of the most design and parasitic intensive parts of the system, which is the receiver and the PHY. And so conceptually, it's a pretty simple thing to do, is to add loopback. In practice, it's something that requires a fair amount of preparation and work. But there really isn't going to be any other way to be able to characterize a design and verify it against the spec without this kind of receiver testing. So we get into what are the actual things that are going to need to be designed and tested. What are the things that implement these technologies that you're going to have to deal with? And fortunately, that's not changed much, and it's not likely to change much with the next generation. Of course, you've got the memory device for servers, which is a very important market. Of course, you used to have buffered DIMMs, starting with DDR3, with DDR4. They added what's called a load-reduced DIMM, which adds to the command and address buffer a data buffer device. So basically, no matter how many DRAMs you've got on the DIMM, they will electrically look like a single load on the motherboard. And in fact, that was one of the first architectural steps that were taken to take this eye that was closing and open it back up without having to make these big conceptual leaps to statistical eyes or impulse response-based specifications like we're looking at beyond DDR4. So at these interfaces, some of them are running at high speed, some of them are running at lower speed. Obviously, signals like reset, would be very low speed, and the data bus will be at the highest speed. And so the kinds of the way the spec is written for each of those and the way the measurements need to be done is going to be largely driven by the speed at which they operate. So on the device, given that let's say you're going to have this kind of equalization circuitry in the device, it's going to need to exist in both the memory and the support logic. And so the things that are going to show up on the data sheet are going to be things like when you set DFE tap, what does it actually do? Does it feed back, X millivolts to a summing junction with if it sees a 1 Y millivolts when it sees a 0, or does it just apply some sort of a gain, a dB based spec? Going in, there's going to be there's linear part, which could be a variable gain amplifier or CTLE. It's got various knobs that need to be set. That'll show up in the data sheet. You should be familiar with the VREF settings, VREF offset settings from DDR4. Clearly, you're going to want to know if you say I want X amount of offset on the VREF. That's a signal that's buried inside the DRAM, and there needs to be a way to measure that. There are improved ways to do it over what was assumed with DDR4, which is basically looping that signal back out a data pin. But that goes beyond the scope of what we're talking about here. In a DFE, decision feedback equalizer, there's an element that basically adds up the feedback from each of the taps. That's going to have a certain bandwidth on linearity. There's going to be crosstalk inside the chip that's likely going to have to be limited by the specification. ODT, what the actual eye looks like at the ball or inside the DFE. And then kind of the bottom line measurement, which is if you think you've found the right settings for everything, what kind of eye can the device itself actually deal with? So one of the first things that has to be done here is basically take everything that's in the data sheet and figure out how to confirm that either your DIMM or your logic device is meeting that requirement. At the system level, there's a whole bunch of stuff that is involved with these higher speeds. Training is getting more and more complicated all the time. With DDR1, basically you had controlled and Z-cube training. That's the controlled impedance buffers. DDR2, 3, 4, every time we've upped the speed, there's been additional training sequences required. Those are basically search out and optimization algorithms. And when you see something go wrong, it's often because the algorithm made an assumption that's not valid for a particular system that you plugged a memory device into. And troubleshooting that has always been a challenge. That's going to be even more so as the speeds go up. Again, there's the actual receiver eye requirement, either at the ball or the output of the equalizer. There are a set of data sheet specs that describe what kind of signal the DRAM needs to see apart from this eye. You can do these measurements on a test fixture with just a device, but mostly these are done in a system where you've got a real controller driving a DRAM, and you want to know, is the signal that's being sent consistent with the spec? The characteristics of the channel and the kinds of impairments and stress that the physical implementation, the motherboard generates, are all things that will need to be measured in a real live operating system. So let me pull all of this together here, leave some time for questions if you have any. Starting with DDR4, I think we've hit a new zone here where basically each generation of DRAM is forcing us to cross into a new threshold of signaling technology. And so the days of being in the old comfort zone and being able to just look at smaller numbers and deal with smaller numbers for things like setup and hold time are really going away. And this is even true for embedded designs as they start having to look at going from DDR3 to DDR4. Now, these concepts may be new to memory, but they're really not new, in the world at large. So just as concepts were drawn from PCI-Express and could be leveraged into a memory architecture to allow an increase in speed, there's a decades of experience in understanding how to do those kinds of designs, how to characterize, measure them, and troubleshoot them. So even though this is new to memory, this is not a problem that hasn't been solved. It's just never been applied in this specific context. And memory is different enough that it requires kind of a merging of the understanding. You have to be able to fuse concepts from the digital and the microwave or RF world as you reach these kinds of speeds, and then you have to apply it to the specification, how you design your hardware, even the algorithms that you're going to put into your controller that describe things like control things like training sequences and so on. So if this happened for going from DDR3 to DDR4, and it's almost certain to happen going to DDR5, what's going to happen beyond this? Is there going to be a DDR6? Well, nobody really knows. But to be honest, I expect that we're in this age now where if there is a DDR6, there's probably going to be a whole new set of rules that we're going to have to understand and be able to apply. So from a characterization and test standpoint, and a design standpoint, you really have to take a holistic approach to these technologies. There's power management is something that's become, power is everything now, pretty much, in memory systems. So that's going to become a much more visible part of the technologies. You've still got logic and protocol. You still need to be able to probe the signals. Test fixtures are going to become a lot more critical, and perhaps, if not formally standardized, reference designs are going to become more available so that people can get reproducible results on each side of the ocean. You've got traditional transmitter measurements made with the scope. We're adding now receiver measurements that would be done with the BERT. And then, of course, the modeling and simulation for design. All of those things have had to adapt to these radical changes. Let's say you lived in the receiver test world. You're used to high-speed serial. Well, DDR is a whole different world. And so you can't just take what you did, say, for PCI-Express and drop it in for DDR. So the whole concept of what the measurements need to do and the kind of measurements need to be made, they have to change as well. And so everybody's in the same boat here. It's really key that folks participate in the standards development work in groups such as JEDIC so that they can get the longest run-up time to understand what's coming and prepare themselves to really know when to make the jump and how to get the most out of these DDR4 and DDR5 designs that you're doing. So if you want to bone up on this, there's a bunch of stuff that you can find on the web. Here's some pointers to things that deal with articles that deal with the different concepts that I've talked about. And I think if you do a web search, there's a bunch of other, of course, there's going to be a wealth of information on these new concepts. So with that, hopefully I've helped you at least understand how to get ready to make the most out of your designs, and I can open it up now to questions.
Thank you. Now we'll jump right into Q&A. If you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we are answering your questions, please complete the feedback form, which is located on the bottom of your screen. Here's our first question. I missed it. Was the DFE expected to be the same over the whole channel, or is it per byte or per lane?
It's conceivable, and I can't say that anything's been decided or proven, but it's quite conceivable that the receiver settings might need to be different per bit. If you look at the variances that can exist in a motherboard design, or even within a standard raw card, it's quite possible that the settings might need to be adjusted per bit, or it could be that they could be adjusted per byte lane with some additional constraints on the channel implementation. So I would say that the jury is out on that.
Okay, here's the next question. Can you talk more about the distinctions between DDR and GDDR?
Sure. So GDDR has always been a generation or two faster than DDR. And the reason that it's been able to do that is because it lives in a world where there are much higher power and cost budgets available to it. So it's been able to assume that a lot more attention is paid to signal integrity at the system level, and so can keep the eye open at the DRAM. And generally, so GDDR doesn't go through a cheap connector, a DIMM connector. The interconnect is very short, but they were the first to have to apply things like a statistical model and a receiver mask based specification to their design. So the main difference really, though, boils down to there's a handful of suppliers and a handful of producers, and they can interact very closely. It's much less of a commodity, if you will, than DDR. They also have a higher cost and power budget to work with, which really opens up a lot of flexibility in the design. And that's how they've been able to achieve higher speeds. Increasingly, you can see this, there are concepts that are proven in GDDR that have migrated into DDR over time, and that's going to continue, I'm sure.
Okay, what will be the peak bit rate of DDR5 in gigabits per second?
Well, that's I would say that's a complicated question. Actually, it's pretty simple. So traditionally, as you've gone from DDRX to DDRX plus 1, the goal has been to double the bit rate. So logically, if you have DDR4 up to 3.2 gigs, you can expect DDR5 to target up to 6.4. The other thing, though, that's true is that there hasn't been a memory step yet that hasn't overclocked. And so you can get DDR4 DIMMs today that claim to work above 3.2 gigs, if you're working in a overclock optimized system. It's quite possible that the same thing will happen with DDR5. So what its ultimate data rate is impossible to say right now, but if the past is any guide, it's going to be 6.4 or faster.
Okay, here's the next question. Scopes and bit error rate testers tend to have 50 ohm input and output terminations. DDR4/5 has variable terminations. Do you see this limiting the accuracy of test solutions here?
Actually not. There's always been defined in the spec in the data sheets a test load, and that's where all the device parameters are measured. It turns out that that has been long defined by what production test equipment can do, and now it's set at a 50 ohm load. And with an ODT value, one of the ODT values is 48 ohms. That is close enough to provide really accurate measurements for device characterization. In a system environment, of course, all sorts of different ODT values are going to be encountered. And that is where things like de-embedding capabilities that exist in the scopes can come in very handy to correct what's physically acquired, to map it into something that looks more like what's in the data sheet. It's not necessarily as simple as all that, but that's basically the approach that's been used and will need to be used.
Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Keysight for sponsoring today's event, and of course all of you for joining. Have a great rest of the day.